The Xi'an JH-7 Flying Leopard is a twin-engine, supersonic fighter bomber designed to deliver long-range maritime and land attack strikes under contested conditions. Created during a period of rapid transformation in China's military doctrine, the JH-7 reflects a requirement to project power beyond coastal waters and defend vital sea lines of communication. Its development was driven by the need to replace outdated attack aircraft and provide the People's Liberation Army with a dedicated strike platform capable of carrying modern anti-ship and precision-guided weapons. In modern air warfare, the JH-7 represents China's transition from legacy designs toward indigenous, mission-specific combat aircraft optimized for regional power projection. 2. Origin and development. History. The JH-7 originated in the People's Republic of China and was developed by Xi'an Aircraft Industrial Corporation. The program began in the early 1980s, as China sought to field a modern strike aircraft comparable in role to Western designs, such as the Panavia Tornado and the McDonnell Douglas F for Phantom II. The aircraft was intended primarily for the People's Liberation Army Air Force and the People's Liberation Army Navy Air Force. The first prototype flight occurred in 1988. Development was prolonged due to technological challenges, particularly in avionics and propulsion. The JH-7 entered limited service in the early 1990s, while the significantly improved JH-7A variant entered operational service in the mid-2000s. It replaced older platforms such as the Harbin H-5 and Nanchang Q-5 in the Maritime Strike Roll Dock 3. Design philosophy and airframe. The JH-7 was designed around the concept of long-range strike rather than air superiority. Its design emphasizes payload capacity, stability at low and medium altitude, and endurance over maneuverability. The airframe is constructed primarily from conventional aluminum alloys, with limited composite materials introduced in later production batches. The aircraft features a mid-mounted swept wing, twin-engine nacelles, and side-mounted air intakes optimized for high-speed flight. A tandem-to-seat cockpit supports complex strike missions, dividing workload between pilot and weapons systems officer. Visually, the JH-7's large fuselage, wide wingspan, and prominent intakes give it a robust, utilitarian appearance. 4. Engine and propulsion system. The JH-7 is powered by Xi'an-built WS9 Kinling turbofan engines, derived from the British Rolls-Royce Spey Mk202. Each engine produces approximately 54 kilonewtons of thrust dry and about 91 kilonewtons with afterburner. Early prototypes relied on imported Spey engines, while later aircraft transitioned to domestically produced versions. The twin-engine configuration provides sufficient thrust for heavy strike loads and improves survivability over water, while adequate for the aircraft's mission profile. The engines do not provide exceptional thrust-to-weight performance compared to modern multi-role fighters. 5. Speed and flight performance. The JH-7 has a maximum speed of approximately Mach 1.75, equivalent to around 1,800 kilometers per hour at altitude. Cruise speed varies by mission profile, but is typically subsonic to conserve fuel. The service ceiling is approximately 16,000 meters, or about 52,500 feet. Rate of climb is moderate, reflecting the aircraft's weight and strike-oriented design. Maneuverability is limited compared to air superiority fighters, and the JH-7 is not intended for sustained air-to-air combat. 6. Range, endurance and fuel range is a core strength of the Flying Leopard. Combat radius is estimated at approximately 1,500 kilometers, depending on payload and flight profile. Ferry range exceeds 3,500 kilometers with external fuel tanks. Internal fuel capacity is substantial, supporting long-distance maritime strike missions. The JH-7 is equipped with aerial refueling capability via proband drogue systems, significantly extending operational reach for naval and long-range Air Force missions. 7. Fuel consumption and operating cost. Precise fuel consumption figures are not publicly released, but the aircraft's large engines and heavy airframe result in high fuel burn compared to lighter fighters. Operating cost per flight hour is generally assessed as higher than single-engine aircraft, but lower than heavy strategic bombers. Maintenance demands are significant due to twin engines, complex strike avionics, and maritime corrosion exposure for naval units. Logistics complexity increased during early service due to engine reliability issues, which improved with the JH-7A variant. 8. Avionics and sensor systems. Early JH-7 variants were equipped with relatively basic avionics by modern standards, including mechanically and radar optimized for maritime targeting. The JH-7A introduced significantly upgraded systems, including improved radar, digital cockpits, and enhanced navigation and attack computers. While not equipped with AESA radar, the aircraft integrates radar, electro-optical targeting pods, and electronic warfare systems sufficient for its strike role. Defensive avionics include radar warning receivers, electronic countermeasures, and chaff and flare dispensers. These upgrades substantially reduced crew workload and improved situational awareness. 9. Weapons and payload. The JH-7 can carry a maximum external payload of approximately 9,000 kilograms across multiple hardpoints. Air-to-ground weapons include precision-guided bombs, unguided munitions, and anti-ship missiles such as the YJ-82 and YJ-83. Air-to-air capability is limited to short-range missiles for self-defense, including variants of the PL-5 and PL-8. All weapons are carried externally. There is no internal weapons bay. This payload flexibility allows the aircraft to perform maritime strike, interdiction, and limited close air support missions. 10. Stealth and survivability. The JH-7 is not a stealth aircraft. Its radar cross-section is relatively large due to its size and external stores. Survivability depends on standoff weapons, electronic countermeasures, escort support, and operational planning, while effective against legacy threats. This approach is less viable against advanced integrated air defense systems. 11. Real-world service and combat use. The JH-7 has been operated exclusively by China, serving with both the People's Liberation Army Air Force and Navy Air Force. It has not been used in confirmed combat operations. The aircraft has participated extensively in military exercises, particularly in maritime strike and joint operations. Official assessments emphasize its long-range strike capability, while acknowledging limitations in air combat performance. 12. Cost, production and global impact. Exact unit cost figures are not publicly disclosed. Production numbers are estimated to be in the low hundreds across all variants. The JH-7 has not been widely exported, reflecting its specialized role and China's focus on domestic deployment. Its development contributed to China's growing aerospace industrial base and informed later multi-role aircraft programs. While not a global export success, it strengthened China's regional strike capability. 13. Strengths and weaknesses. The JH-7 excels in payload capacity, range, and maritime strike capability. Its weaknesses include limited maneuverability, lack of stealth, and avionics that lag behind modern fifth-generation fighters. Criticism has focused on engine performance and survivability against advanced defenses. Like all aircraft, it represents a compromise shaped by doctrine, technology, and strategic priorities. 14. Final verdict. The JH-7 Flying Leopard represents a critical step in China's evolution toward indigenous strike aviation. It bridged the gap between outdated platforms and more advanced multi-role fighters, While not a frontline solution for future high-intensity warfare, it remains a capable regional strike asset, respected for its mission focus and endurance. The JH-7 stands as a milestone in modern Chinese military aviation,